So this is an experiment that I actually did it last night, okay? It's a solder, and I made some holes on the bottom, and I made a little angle. So what do you think is going to happen when I pull this up?
It's gonna be a little heavy at first.
Is what?
It's gonna be a little heavy at first, and then the water starts to come out as you pull it.
That's it? What else? What do you think is going to happen? Can you imagine?
The water is gonna go down.
The water is going down. The angle of the hole is not straight, it's to the sides, like that. So the water is going to, yes.
Like spin, maybe?
Spin maybe, so let's see, okay? Let's see. Yeah, was spinning, right? You got it. Spinning, let's see. Let's do it again. So this is the kind of thing we're going to study today. The other thing we're going to study is about actually the first experiment we did. We never talk about this one. This is actually a law, right? That when we let this cart move, it's going to move at a constant speed. And if we don't touch it, it's not going to move at all. Who said that the first time, huh? Newton said that, right? Actually, Galileo also said something close to it. I'm going to read what Galileo said and then what Newton said for you, okay? So Galileo said, a body at rest remains at rest, and a body in motion continues to move at a constant speed along a straight line unless acted upon by an external force. Isn't that what we see really here, right? So if this thing, assuming there is no friction, right, is going to be moving continuously, right, forever. And if it's nothing acting on it, it's not going to move. So that's the first law of Newton, right? Newton said basically the same thing. Every body perseveres its state of rest or of uniform motion in a right line unless it is compelled to change that state by forces impressed upon it. So this is part of my notes. I think I already posted. I want you guys to read this and reflect and connect with this experiment that we did in class. What do you guys think about this law? Is that something you accept, agree, or what do you think?
I mean, he's a scientist, so.
You what?
He's a scientist, so.
You know, it took me a long time as a student to understand that. You know, when I chose to study physics and I had this class, I just didn't believe it because I never saw anything moving continuously. Have you seen anything moving continuous like that?
Only in space.
Huh?
Only in space.
Only in space, right? Because your generation have seen men in space. When I was going to school, you know, I didn't have that, right? I never see anybody on space throwing, you know, toothpaste, and the toothpaste was moving, you know, like this, and the other grabbed. When I saw that, I said, oh my God, that's my class. I saw that, you know. Now I can see that for the first time. But before, you know, I was fighting my professor and asking him questions. And I was, you know, very annoying. I remember that. 'Cause I don't see this happening. When I throw something on the floor, it's going to stop. Why are you saying this thing is going to move continuously? It took me 1 year to, you know, start understanding, you know, the first law of Newton. The other one, yeah, I can accept that. You know, if nobody touched the car, it's not going to move. But, you know, come up with the idea that this thing is going to be moving forever, it took me some time. Okay? So it is not part of our daily experiences. That's why, you know, for me it was difficult. The other thing is the first law of Newton doesn't hold for every reference. So let's say I'm here with this car. I'm sitting here on the top of the car, okay? And I'm accelerating, okay? I'm driving my car on the freeway and I'm accelerating. You all drive cars, right? When I was a student, I didn't have a car, so you know, I didn't have that. So when you accelerate, what happens? Do you feel something with your back and the seat, right? You feel something. You feel that there is some force acting on you, right? So I'm driving and I'm feeling, and you sitting here watching me driving, being accelerated, and okay, you are here, and I'm sitting there, and you ask me, hey Eugene, do you feel the acceleration? And I say, yes, I feel it. I'm driving, you know, I'm feeling this thing in the back pushing me, you know, and I see you from my car. I see you there, moving. You also moving, right? Because I'm sitting there. I'm, you know, in relation to the car, I'm not moving. But you are sitting here on the ground, and you seems to me that you are moving. And then I ask you, are you feeling the acceleration? No. Right? I'm not feeling anything. So the force is only there, it's not here. So, it also has this concept of the inertial frame of reference, right? You've got to be an inertial frame of reference to be able to see this acceleration, right? But there is no frame of reference without acceleration, right? Is the ground a good frame of reference? Right here, this ground, is this, are we not being accelerated?
We are.
We are. Why?
Because the gravity, and also there's another gravity that's pulling up. There's two different gravities.
Well, gravity is only moving this way, right? And I'm not moving that way.
Or normal force and gravity, sorry.
No force of gravity, but what else is there?
We're all spinning right now.
We are always spinning right now, right? It is true we didn't cover circular motion, so you shouldn't be able to understand, you know, that, you know, in order to have a circular motion, you have to be accelerated. But yes, the Earth is spinning, right? In addition to spinning, it's also going around the sun, right? It's also, there's a circular motion there. So there's no real inertial frame of reference, okay? So that's why it's difficult to prove Newton's law, to prove, right? But it works, yeah, it works. every time we do some calculations, we find, you know, answers. We can solve our problems. Now let's talk about a different problem now. Let's talk about, let's suppose I have a spring, and here I have a block. If I move this block away, what do you think is going to happen?
The spring stretches.
The spring is going to what? Pull back, right? So we're going to have a force here, and this is M1, and then we're going to have a force there, right? The spring is going to be, they have this pull, right? Try to bring this to the center, and we're going to measure some acceleration. So M1 acceleration, 1. Now I change the block to M2, and then I'm going to measure another acceleration, right? Acceleration 2. Now, M2 is 10 times larger than M1. What do you think is going to happen to the acceleration? Okay, here is Eugene sitting here, okay? I'm 200 pounds, and there's this spring here, right? Pulling me that way, right? So I'm going to be accelerated. Now comes Aram. Aram is a skinny guy, right? He's 100 pounds. Who's going to be accelerated? He's going to be accelerated twice as much, right? Because he's half my weight. So it turns out this is a fact that M1A1 is equal to M2A2. Okay? And that is what we call force. That force is proportional to the acceleration, right? And the constant of proportionality is this thing that we call mass. That is the second law of Newton. Okay? Now, if I'm holding this ball like this, right? What is happening? The ball, if it were not for my hand, the ball would fall. But because I'm holding this here, right? This is in equilibrium right now. But the ball is exerting a force on my hand, and my hand is exerting a force on the ball, and is holding that there. So let's make a diagram for that, right? So this is F of gravity, mg, right? M is the mass of the ball, so I can make a force diagram like this. So this is the force of Earth on the ball, and here is the force of my hand on the ball, right? So it's balancing out. Now, there is also this concept of a system. When we talk about a system in physics, we isolate the ball. The ball is the system that we're looking for. Okay? Everything else we call the environment. When we study the ball, we just focus on the ball. So let's do a different problem. If I have, let's say I have a table now. I have a table, and here I have a book, book A, and here I have book So it's important to learn how to draw a force diagram. So what would be the force diagram? If we consider the system A, so A is the system that we are looking for, we are focusing on A, so how are we going to describe the force diagram? Can anybody help me to do that? Yes.
So you do like a free body diagram.
So the first thing, I'm going to consider A as a dot,
Mhm.
right? A point, and then what do we do now?
You put the forces that are put on there, so you put the force of gravity going down onto there, and then the force of the
Okay, gravity, okay, let's do that. So we're going to put that down like that, and that is the Earth, the force of Earth on A, right? That's the gravity.
And then you put the force of the book on the B on book A.
Then B on A is going to also be coming down, right? Force of B on A. So this book is heavy and is on top of A, so it's putting some force there. And now,
And then you put the force of the table on the book.
table on A, right? And that is going this way, force of table on A. Excellent. So, what do you think the sum of all these forces should be? 0, right? The force of all, the sum of all these forces has to be 0. Why?
Because it's not moving.
Hmm?
Because it's not moving.
It's not really because it's not moving. That's not right.
It's there.
It could be moving at constant speed, and the sum of the forces would still be 0. If it's moving at constant speed, the sum of the forces should be 0.
Is it because it's not accelerating?
It's not accelerating, no. It is in equilibrium, it's not going up, it's not going down, right? But if it's falling, right, that's being accelerated, that's different, right? And if it's moving in that direction, and it's being accelerated, then you have to have a force there. But in this case, because it's in equilibrium, and we write the sum of forces like this, we have this symbol here that means the summation of all forces is equal to 0, okay? So I have to write down that Ft on A is equal to Fb on A plus Fe on A, right? Has to be equal. So if a body is moving at constant speed, again, what's happening in terms of forces? The sum of forces is equal to 0, right? It's not being accelerated. If it's being accelerated, what is the sum of forces equal to? If it's being accelerated,
Still 0.
it's equal to ma. Right? It's being accelerated, it has an acceleration, it has a force being acted on the body. So it's going to be equal to some force, and that is m times a. If acceleration is 0, m times a is 0, right? There's no acceleration. Okay? Again, so constant speed, sum of forces is equal to 0. If this is being accelerated, it's going to be equal to ma, right? To a force. We don't know how much it is. We have to measure the acceleration, okay?
Are we learning about force now?
Yeah, well, we just learned about force. We learned about, first law of Newton. What does first law of Newton is telling us? Do you remember?
I do, but I just don't remember the guy's name. No, the scientist.
Yeah. The first thing we learn is that a body is not going to move by itself, right? If it's at rest, it's going to stay at rest until a force acts on it. And once this force acts on it, this thing is going to start moving. The force is not acting on it constantly, continuously. It's just act at one spot there, and then the thing is left going along, moving along at a constant speed because there's no force acting on it. And it will be moving forever. Okay? Until somebody stop it, right? Apply some force to stop it. Or if there is friction, right? If there is friction working on it to get to stop, it will stop. And that's what happens in our experiment in reality, because, this is not, there's no car without friction here. There will be always some friction there. Okay? So that's the first law of Newton. The second law of Newton, we showed that, what is that drawing? Oh, I erased it, right? The one with the spring and different masses, M1 and M2. They both will be accelerated, but if M1 is 2 times M2, the acceleration when we measure is going to be 2 times less. So the product is a constant. M1 times A1 is going to be equal M2 A2. This product is constant. Force is proportional to acceleration. And that constant, right? Force is a vector. Acceleration is a vector. But mass is a is what? Is mass a vector?
It's a scalar.
Scalar, right? So a scalar times a vector is another vector. Okay? About the third law of Newton, like I'm holding this ball, right? The ball is acting on my hand, and my hand is acting on the ball, right? It's called action and reaction, right? To every action, there is a reaction. Be nice to people, people are nice to you, right? What is this here? Which law is determining this movement? Which law? Huh? I didn't hear you. The first law? This is called the hero's engine, right? It's called the hero's engine. So let's discuss that. Which law? We covered 3 laws today, right?
Would that be the second one?
You think it's the second one? So, I'm disappointed today that George didn't bring his skateboard. I was coming driving, yes. Today, I'm going to use that skateboard and I'm going to be flying there, okay? I was going to sit on that thing and just move. And I was going to ask George, just push me. And he was going to push me and I was going their way, right? And let's say he has a skateboard too. We both bring 2 next class. We're going to do that experiment. We both are going to hold each other and then we're going to do like this. Where do you think it's going to happen? We go in opposite direction, right? So action and reaction, right? So which law is making this thing spin?
Action, reaction.
Yes, action and reaction, right? The action of, this is like the jet engine, right? Pull this way and move this one the other way, right? Like a,
A rocket.
rocket, right? Thank you, yeah, like a rocket. It's action, this is it. So you can make a little motor out of, if I had not made the holes a little twisted, just straight was not going to move. If I had made straight, was not going to move because, it would be just water coming out. But because I kind of twisted the hole going this way, so it moves out and then makes you spin, right? By the way, this is a Brazilian soda, so.
I was gonna ask. What kind of soda is that?
It's just like a, 7-Up or something. So let's move now to this one here, okay? So here, the equilibrium of forces. So what do you guys think? This is about 200 grams going this way, right? And here I can measure 300. So let's make some notes. See if we can calculate that and make sure the readings are correct. So let's make that diagram. The angle is not the same, it's a different angle. So we have this one going like this and the other one going like that. And here I have 200 grams. Here I measure 300 on the highest one, 300. And then here I measure 150. 150. Does anybody has a way to measure the angle? Well, we have this thing here, we can measure the angle. So if this is 0, 0, so this is 25 here, 25 degrees. And let's measure here how much is going to be here. 60. Okay, so this is one problem. Please copy that. Can you guys read this? Are you able to read? All right, so now I'm going to change this, and I'm going to bring this at the same height as the other one. So here I see 45, and here see 45. Now it's 45. But it doesn't look right to the center. Here I right, what do you guys think is gonna be the readings now? What about the reading here? Is it gonna be the same? How much I have here? $200. It's still the same. It didn't change. I think that's expected, right? Here is still 200. What about here? What do you guys think is gonna happen here with this two? This is 45 now, and this is 45. Any guess? What's gonna be the reading here?
They'll each carry an equal amount of weight.
Huh?
They'll each carry an equal amount of weight.
Equal amount. So here I see 200. I read 200 on one side and 200 on the other side. Okay? All right? So, any suggestion? How can we check this? It should be the sum of all forces here should be equal to, huh? 0, right? The sum of all forces should be equal to 0. So, is it fair to say that I can calculate the x components and the y components? So the x components should add up to be 0, right? Because it's not moving on the x-axis. It's not moving on the y-axis. So the y component should also be 0. So let's write down here what would be, and by the way, we don't call these forces, we call these tensions now. So we're going to call T. Because on the string, the force is like tension, right? You feel a tension on the string. So we're going to call that T now. So T here is 300. What is the angle here? What is the angle here? 60, right? So this component on the x-axis is going to be what? Let's say this is T1, this is T2. It's going to be T1 cosine 60, right? And that is going to be equal to T2 cosine of what?
25.
25, okay? But T1 is 300 cosine 60 equals 150. That's what's the reading, cosine 25. So let's see if that's it should be equal, right? Let's see if that's close enough or not. So let's see. Cosine 60 cosine. So that's half times 300. So this side here is 150. Let's see that side. It's not going to be 150 because this is 150 already. So let's see, 25. So I got here 136, okay? That's on the x components. Maybe I make these readings a little better, but you have to remember there is some error here, right, on this string. Let's do now on this side and see what we get. This is 45. This is 45. Oh, we need to finish here. We need to do the y-axis, see what's going to happen. So on the y-axis, I'm going to have T1 sine of 60 plus T2 sine of 25, and that should be equal to 200, right? Because I have this component here going up, and the component of T2 going up, it should be equal to 200 is coming down. So it should be a balance here, right? So T1 is 300 times sine of 60 plus 150 sine of 25, and that should be equal to 200. So let's see, 60 sine times 300, that's 259. And then 25 sine times 150. Yeah, that was not right at all. Is that correct? Yes, 300 here, and sine of 60. That's 63, so that's more than 200, okay? What about this one? Let's do this one. 45 cosine times 200 is 141. 141 plus 141 is going to be like 280 versus 200. It should be balanced, but you know, because of all the arrows here on the angles and on the spring, it didn't match. It was not, you know, an experiment that confirmed that. But believe me, you know, it has to be zero, okay? The sum of all forces. Okay, so let's stop here and then do some experiment. Let's have a break and then see if we can do some experiment today.